오늘 저는 이제 2018년 튜링 상 수상자이신 이 제프리 힌튼, 얀 르쿤, 요슈아 벤지오
So, this 2018 Turing Award laureates were Jeffrey E. Hinton, Jan Lecun, and Joshua Bengio.
표현하자면은 아마
Just to
이렇게 될
sum
것
up
같아요.
their achievement, and it would be deep neural network, which is very a critical component for
이끄신 데에 큰 공을
deep learning
세우셨다라고 저의 오늘 세미나에
of components of computing.
한마디 한 줄 그 메시지가 될 것
So I
같습니다.
think that could be
한번 시작해 볼게요.
essence of what I'm going to talk about today.
AI 뭐
So
지금
when we
너무
talk about
떠들썩하죠.
AI, it is
저희
something that
사이언스나
everyone's talking about,
소사이티
and
모든 면에서
it
AI가 많은
is
것들을
very
변화시키고 있다고
influential, and it's
생각합니다.
transforming our science field
콘텐츠에서는
as well as our
스피치
society when it
뭐
comes to
드럭
speech
디스커버리라든지
recognition,
애스트로노미,
astronomy,
사이언스까지도
and even into
엄청나게
our
변화를
science.
일으키고
It
있습니다.
is bringing a huge
AI가
transformation.
이렇게 엄청난 성공을 거두고 있는
So the
것은
reason why the AI was able to be successful was that because of this technology called deep learning. Then what is deep learning? How can we define it? So I asked it to Google Bard, which is a generative like ChatGPT, sort of like a generative ChatGPT, and I asked it to Google Bard, and it said that deep learning is a subset of machine learning that uses artificial neural networks to learn from data.
많은 분들 사실 참석해 주신 분들 잘
And I'm
아시겠지만
sure that many of you knew about this definition, and I thought it made sense.
사용해 보신 분들은 더 잘
And
아시겠지만
those of you who used it
시스템들이
may fully
저희
understand
사회의
what I'm
많은
talking about.
부분들을 변화시키고
And it's
있습니다.
been transforming a lot of aspects in our
그런데
society.
이 세 분이
And these
딥러닝의
three
발전에 혹은 딥러닝을
godfathers,
집착하신
like who have pioneered a deep learning domain,
아이덴티파이 하고 있는 건데요. 이분들께서 사실 같이 일을 많이 하셨어요.
and they have worked collectively together. They were like professors and the students. They have worked together for at least 30 years, and Professor Hinton has dedicated his 50 years of his life on deep learning.
딥 네트워크의 어떤 개념적인 것들을
And they have also established this conceptual foundations for deep networks, and also identified a lot of interesting phenomena, and also developed engineering advances in practice.
그런 것들이 있겠습니다.
But there's this one thing that I want to share with you. This deep learning, its development wasn't always easy, even from the beginning. So that is why I'm going to delve into the history of deep learning. And if we go back to the 1950s, and the reason why I want us to go back to 1950s was because that in 1950, Alan Turing asked a question about what is intelligence and how can we realize that our human intelligence on computer. And so he came up with this concept that if these machines pass this some kind of test, then intelligence can be realized in computers or on machines. So there were two paradigms since 1950s. First was symbolic AI, and the other was the connectionist AI. So symbolic AI, simply put, is that
사람이 이해할 수 있는 어떤 심볼 같은 걸 사용해서
So they utilize these symbols that humans can easily understand, and based on logics, they create this
아주
intelligence.
간단하게 한마디로 하면 프로그래밍입니다.
So
어떤
it can
이해할 수
be
있는 언어로 로직을
understood
짜서
as programming.
일이 벌어질
So
때는
we
이렇게 해라.
design
저렇게
and we
이루어질
do the
때는 저렇게
programming
해라.
and
이게
make
로직 베이스드
the
심볼릭
orders,
AI라고 하는
and that is
심볼
also
AI라고
thought
할
of
수
as
있고요.
the logic-based
connectionist
symbolic
AI는
AI.
뭐냐면요.
And
이
connectionist AI, on the other hand,
그게 아니다.
is that they
우리는
are kind of
어떤
arguing
커넥션만 있으면
against
된다. 그
symbolic
커넥션이
AI, and they're saying that we need some kind of like make a connection that is similar to some kind of like like neural network
얘기고 결국에는 이
of
어떤
life
뉴런들을
beings.
입고 있는 커넥션들의 스트렝스를
So
학습하기만 하면
and they
된다.
just need to learn the
라고 얘기를
strength
해요.
of
그래서 우리는 학습을 해야
these
된다.
neural networks.
인텔리전스는 학습을
So
통해서
this
형성하는
intelligence can
것이다라고
be
주장하는
created through learning.
파라고 볼 수
So
있겠습니다.
these were the group of people who said that intelligence can be learned through
그런데 이제
adjusting
정답을
the
먼저
strength
얘기를
of these
하면
networks.
정답이랄까요? 지금 현재 답을 얘기를
But just to
하자면요.
give you the answer
AI는
of who's right, like whether the symbolic AI or the connectionist AI, is that if one picture is given, then symbolic AI can't solve it.
일어나고 있느냐를
And if we ask them
제대로
what's
설명을
in the
못합니다.
picture and what's happening in the picture, then they can't explain it
하이 레조루션
just by simply.
이미지에서는 픽셀의 뭐
And so for high
가속도가 뭐
definition,
빌리언
like
단위로
images,
어떤 픽셀이 들어왔을
like the
때
pixels
어떤
goes on the
아웃풋이
millionth,
이거 코딩하기가
which is
어려워요.
about going beyond millionth.
그런데
So
이제
it is very
러닝
difficult
리서치
to
혹은
solve
뭐
that.
커넥션ist AI
But
같은
in
경우는
case of this connectionist AI,
여기 사진에서 보는 바와
and as you
같이
can see in
단순히
this
어떤
picture,
오브젝트만 레코나이즈하는
they
게
just
아니고
don't they
어떤 감정을
recognize
느끼고
beyond
있느냐,
the objects, and
왜
they
그러느냐,
also
그런
recognize
어떤
the
휴머니티 같은
objects, the
것까지도
feelings,
이제
and they can
capture할 수
capture
있거든요.
the moments, the
근데 처음에는
subtleties like moments.
이게 가장 중요한 퀘스천이었어요.
So in the
커넥션만
beginning,
있으면 된다고 했는데
this was the
과연 그
most important
커넥션
question,
스트렝스를 어떻게
was that
학습할
then
것이냐.
how can they train themselves
그게
on
이제
these connections of the networks?
이제 풀어야 하는 숙제였던 겁니다.
So that was sort of like
물론
a
이제
homework
뭐 튜어링도
that the
포함해서
scientists had to
어떻게
solve.
약간 시도해보고 이렇게
So just
한번
like
해보고
Turing,
만약에
they
이게 좋지
could have
않으면
done a lot of like
버리고
trial and errors, and they could have kept some of the outcomes that was good, and throw away, get rid of the ideas or the things that did not turn out to be well. So the first thing that came out, which was the initial model of neural network, was perceptron. So if there's a lot of input signals,
신호를 받아서
then those signals are being received and being associated, and they could, send it to the response units. And it was called using the activation function. And so through that, and this guy named Rosenblatt, he is the one who suggested such idea. And so these machines could learn, but those like features could not be learned by machines, and they could only learn the features that were given by the humans, and they could make outputs based on those features given by humans. So in the year of 1969, Marvin Minsky, who was the founder of MIT AI Institute, and he made this paper on created a paper on perceptron, and he criticized perceptron and said that, I know that there are a lot of like strong limitations on perceptron because it becomes complex, then it cannot be able to solve those problems. And so that is why the first neural net winter has begun in the year of 1970s. So this neural network kind of lost its traction after Minsky's paper came out. And from the mid 1970s, several people suggested about this idea called backpropagation that was in the 1980s.
어떻게 학습해야 되느냐?
And so there was a huge question of like how can these machines learn when there are a lot of neurons? Because there were a lot of like methods such as like mutation methods and reinforcement learning methods, but they could not train these machines if there were a lot of like neurons. But when this backpropagation idea came out, these connectionist AIs like hurried, and because it was able to bring up really good performances, because when it came out to some of the like image recognition things, assignments, then they were able to perform well. So let me just give you a brief explanation about what neural network is. And this is something that was first proposed by McCulloch-Pitts neuron. So this is sort of like the signal transmission system that is artificially like converted. So if there's soma body and inside the nucleus, it can be send the signals. And in order to express that artificially, so then there's the signal of x1. Then based on how the strength of these signals, which is W, then it all are being associated to create an output. So in case of perceptron, they add activation function to it. But this was the initial model.
뭐랄까 이제 한 가지만 있는 게 아니고
But if there are so many of these different neurons, then
그런 신경 전달
it
시스템을
could
닮은 아티피셜 뉴럴 네트워크다 저희가 얘기를 합니다. 이 경우는 이제
be translated into an artificial neural network. So because humans also have so many different neurons, so what the connectionist AI did was that when these signals come in, then it moves on to other representations. Then how you're going to adjust those strength was the key to solving this problem, and we just needed to adjust the weight, and based on adjusting these weights, then these machines could learn the features. So then how can we do that? We know that this is a powerful network, so when there are more neurons and when there are a lot more inputs, then they can bring out the better outcomes. We know that this is a very powerful tool. Then how can these machines learn good features, and how can we train these networks? So through supervised or unsupervised trainings, so when there's an input, you need to keep on supervising until it draws an outcome that I wanted. So based on how you have supervised, then the outcome comes out differently. And there's this other mutation method, which is sort of like the reinforcement learning. So based on the outcome that you see, and if you like it, and if you don't like it, then perhaps you can change the weights. But only by changing the weights, it is very difficult to update so many different neurons. So that is why when the backpropagation algorithm was introduced, because you first need to do the forward propagation, and it brings out the prediction for the outcome, and you just have to see like how that expected outcome is close to my expected outcome or the wanted outcome, and you do the back press in order to get closer to the outcome that you want.
정확히 계산할 수 있습니다.
But that
두
outcome
가지만 있으면 되는데요.
can be drawn by exactly accurately measuring by using calculus.
뉴런이 많잖아요.
Because there are so many different neurons that they can have.
병렬적으로 계산하기 위해서
And for us to simultaneously do the calculus of, the computation of this
두 가지가 있으면
neurons, then you'll be able to do the backpropagation.
사용했더니
So when we did the backpropagation algorithm,
뉴럴 네트워크에 이제 부흥이 오는 거예요.
and when we were able to do that, people started to be much more interested in this neural network once again. Because this model started to work properly and well. Because when this neural network was getting larger, it was able to use well at scale through optimization. But even though it worked properly and well, there was a huge disappointment again. Because there were some other approaches like symbolic AI approach and other approaches as well. They were much better in the performance in terms of understanding that logic. So when we wanted to make this neural network larger, we could not have these machines, learn just by using this back propagation. So that was a huge disappointment among the scientists. And during that, the academia, amongst the people in the academia, so a series of conferences and top-tier conferences. For NIPS, when Professor Hinton submitted a paper, but his paper got rejected, and he asked the committee why his paper got rejected, and he got the answer saying that, there were two papers that were submitted for neural network, but there were too many to, accept those two papers. And ICML also rejected, saying that you're not supposed to submit a paper related to neural network. And this another professor submitted a paper related to neural network to CVPR, related to a classification algorithm. And it was sort of doing really well technologically at the time, but it got rejected. And then the reviewer said that in your paper, you try to, so at the frame of mind in computer vision at the time was that if there's an object, then there should be rules for these machines to learn, because we can't explain it. So they all got rejected. And so that is when the second winter for the neural network technology came. And after that, so the deep learning started to revolutionize. So if you look at the timeline, it's not accurate, but it was roughly in the 2010s or 2009, and that is when this revolutionary things happened for deep learning. And Professor Hinton said
데이터의 양이 많아졌어요.
that the reason why we were able to have this boom again for this neural network was because we were able to have huge data, vast amount of data, and computation became much better.
백프로파게이션 알고리즘이 없었던 게 아닌데
Because backpropagation algorithm was existent even before this time,
하려고 했더니 안 됐던 거예요.
but when they try to
여러 가지
make the machines learn, they weren't able to process it.
사전 학습을 한다. 아니면 뭐 어떤 뉴런들을
And of course, there were a lot of trials and errors and at the time as well.
하나만 딱 바꿨더니 학습이 굉장히 잘 되는 뭐 이런 테크니컬 어드밴스들이 있었지만
But
결국에 이것이 이제 세상에 나오고
when this came out to the world, and the reason why it is gaining a lot of
얘기를 하십니다.
light was because of this vast amount of data and because of the advancement of the computing systems as well.
여러 가지 애플리케이션 얘기할 때 뭐 딥러닝 애플리케이션 얘기하면
So when we're talking about deep learning
GPT다 이런 얘기 많이 하죠.
application, they talk about
어쿠스틱 모델링이라는 것이 이 뉴럴 네트워크 혹은 커넥셔니스트 AI의 관점에서는 가장 성공적으로
So this was the first successful task when it comes to the neural network and for the AI connectionist, because
A 뭐 Q 뭐 이런 음절 같은 게 있잖아요.
so
그거를 이렇게 recognize 하는 테스트예요.
so this was to make the machine to recognize the sound of the voice, and Professor Hinton used
다른 뉴럴 네트워크를 사용하지 않은 다른
used,
비교해서 굉장히 좋은 퍼포먼스를
this
보이는
neural network and brought
결과를 내시고
really good performance compared to other technologies. And when that research achievement came out,
안드로이드 같은 거 포함해서 바로 뉴럴 네트워크 베이스로 넘어가기 시작합니다.
and then that's when people started to apply this neural network technology. And for the object recognition, there's this thing called ImageNet.
똑같이 2012년대 챌린저들인데
There were a lot of challengers at the time for the ImageNet,
세계적으로 리딩하는 컴퓨터 비전 그룹이에요.
and they were the world leading computer division groups.
성능을 보이면서 완전히 제가 이때 공부를 조금 했는데
And that is the time when I started to, learn about deep learning.
스위치 돌리듯
And that was a huge event when people started to gain a lot of interest
엄청난
on
마진으로 성능을
this
기록했다라는 얘기고요.
deep
그
learning.
밖에도 이제 계속 이제 많은 도메인, 많은 테스트에서 이제
And even after that, there were a lot of innovative experiments and tasks
이런 시퀀스
on deep learning. So there were this sequence to sequence model, and we also have this thing called a transformer.
비하인드 스토리 좀 들어봤는데 그게 뭐 처음부터 트랜스포머로 하려고 하는 건 아니라고 해요. 뭐 급하게 말을 했는데 어쨌든 한 랭귀지에서
So it is translating from one language to the other. So that is why it is called transformer.
완전히 그 챗 GPT를
And including ChatGPT, it has dominated this language GPT.
이제 이거를 이제 힌튼 교수님께서는 심볼릭 AI를 정말 끝내버렸다.
And he said that this was the final nail in the coffin of symbolic AI, and that was because this translation technology is something that symbolic AI has to achieve. So it is an idea task. Because because of the symbols in and symbols out. But for the translations, symbolic AIs can't solve it, but it can be done through the neural network. So these type of advancements are keep on coming out. And also for the vision, there's a lot of things that we still need to solve. So even if they put this noise, we can see that it can be recognized as panda, but neural network, it doesn't, because if he makes a turn around, then people can recognize it, whereas humans can recognize it, whereas the machines can recognize it that easily. And the other thing was that this is thing that I'm telling you is that all came out from the Turing lectures.
근데 뉴럴 네트워크에 큰 문제가 또 하나 있다.
So there's this another problem with neural network is that in the process of updating this weights through the backpropagation is very artificial. So it is not same as how like humans do that because they themselves need to adjust the speed of the changes to the weights.
또 forward 알고리즘이라는
And made this forward algorithm that came out with so that can be so he proposed this conceptual idea that can be learned without using this backpropagation. So
저는 오늘 그 어떤 이런 historical한
sum it up, like I explained about this neural network's development through these historical events, and we are in this era of like 2020s. And so deep learning is rapidly like transforming science and society, and it has become a very like critical component to our daily lives. And of course, I would like to give this credit to Professor Hinton's lecture that was given through 2019 ACM, FCRC. And I would also like to thank all the participants who are present here today. And also, this is my baby sitting on a baby chair, and I use this Hugging Face API, and I have used that to put my baby's face in the picture. And even if we do that, there are still some errors, so there is still a long way to go for us. So thank you for listening.